So how do we go in then and increase our chances and defeat this program while ASLR is actually running? So let's first load the program back into GDB and take a look at the stack when the program crashes. And we'll use the same command as before, run, and then Python -c, print a times 604, plus our return pointer guess, we'll just put in BBBB again, plus we'll just throw in the NOP sled, times 100, and close that out. So when we run that, we get the segmentation fault at 42424242 again, which is what we expected. Let's take a look at the stack. So examine, X stands for examine, by the way, 20X, reference to ESP register, -4. And we can see at the top our return pointer guess, of course, like we did previously, followed by our NOP sled. So take a look here. This is what we're taking a look at specifically. This is the address on the stack where this is located. If we run it again, take a look at the same area, it changed again, just like we saw with that ESP program, which copies or moves the ESP address into EAX and prints it out on the screen for us. We see that it's changing each time with that 2 to the 20th, just over 1 million entropy pool that we talked about previously. So what's the best way to exploit this? There's a couple different methods in which you can do it. Specifically, there are some vulnerabilities and some functions that you can call. execlong, for example, is known to not re-randomize so well when it replaces the process image. You might be able to reference a local variable through that way. But in our example, we're just going to do a brute force and see how long it takes. Now, brute forcing should work even if the randomization is 2 to the 27th, which is a lot more than 2 to the 20th. It'll still work. It just depends how many tries do you get. Now, obviously, you're going to generate a ton of system logs and you're going to get detected. But if you're doing a red team penetration test, you're doing everything you can to possibly get in. Plus, it all depends if somebody's actually monitoring the logs. So let's drop out of GDB. Now, one thing I'll point out is when you're brute forcing, we're still going to need to use one of these addresses as our return pointer guess, but it can be anywhere within that 2 to the 20th range. We want to increase our NOP sled to make it so hopefully we can drop in there. We don't want to make it too large, and you'll see some reasons why. The first thing we're going to do is drop out of here. I already have the program written, so I'm going to create a range and a for loop of up to 25,000 attempts to defeat ASLR, to brute force it. Once it hits 25,000, it's just going to stop, and we'd have to rerun it. But in my experience, we will get it within 25,000 runs of the program. So the program's already been written. I'm going to set up the for loop and then explain the code as the for loop is running to save time, because the for loop could definitely take a few minutes before it's successful. So let's drop out of GDB. So I'm going to create this loop. So we'll say for I in, and then the range I'm going to use is 1 to 25,000. And we're going to say do echo number of tries, and this is just for me because I like to see it on the screen. And it's obviously going to print out the counter. And then we'll say end. We want to run pw_ASLR is the program that I wrote that I'll show you shortly. And we want to say break. If it's successful and we break out of there or we exit out of the root shell, we want to break and not rerun the loop or continue where it left off. Then we'll say echo exploit failed. So it's going to continue to echo exploit failed on the screen until it's successful. Sleep, we'll just say 0.01. The only reason I'm putting sleep in there is it gets a little overwhelming on the screen, and it's kind of hard to take a look at what's going on if you don't use sleep. So very small value there. Clear, we want to clear the screen each time so it keeps it nice and clean on the top. And then we'll say done. So we're going to go ahead and run this. As you can see, up on the left side, it says number of tries. So it's showing you how many tries it's made so far to defeat the program. We see our ASLR ESP is at this address here. Our return pointer guess is just one I picked out, which is BFFF4D0. And it's doing a little math to calculate the distance between the guess and where the ESP register is actually located for that specific run. Now, this isn't always valid because of the way we're actually wrapping the program, but it's usually pretty close. And it's, of course, printing exploit failed on the bottom. So let's take a look at the program. This is the program here. Up top, we've just got our libraries that we need, of course, our modules that we need to bring in. Here we've got a function called ESP. This function ESP, all it's doing is it's taking the value held in ESP, and it's moving it over to EAX. And then we're going in and using the assembly instruction shift right, and we're shifting 4 bits, and we are doing that to the EAX register. And then we'll be able to use that value. The reason that we're shifting 4 bits there, and I chose to do it this way, is because I need to get rid of that low order nibble. Because remember, the low order nibble is always static. So if we want to be able to do a little math against that, we just need to knock that value out. So this is just the way I chose to do it. Down here we've got our main function. Here's the shellcode that we just used. This is our shellcode that we were just successful with when ASLR was not running. And it simply does a set UID call to restore root, and it also runs execve with /bin/shell, which gets us that root shell on the screen. Down here we've got a buffer. Yeah, it's an odd number of 1643. The reason I chose that, or that number is there, is because we're sending in a NOP sled of 1000 down here, and then we've got our 604 bytes of padding to get to the return pointer. Then we've got the return pointer, and we also have the shellcode down on the end. So it just happens to work out to 1643. These printf statements here are just some information that I wanted to print out. Right here it's saying printf ASLR ESP is at, and it's giving you what is returned back from the ESP function. And then it's saying return pointer guess is at this address. It is then doing the distance, which is simply doing a little bit of math right here and subtracting the real value that ESP is holding from our guess. Again, it's not always going to be accurate, but it's usually pretty close. Down here we've got memset. We're just setting 604 A's to fill the buffer until we get to the return pointer. Then we're using stringcat to go ahead and add on our return pointer guess right here. Following the return pointer guess, we are using memset to put in 1000 NOPs, as you can see. And then memcopy. I'm not sure why I chose to use strcat and then memcopy, but I did. We are adding on our shellcode and appending it to the end of our input. Finally, we're using exec-long to open up the vulnerable program, and we're feeding it in the buffer that we created. So, of course, that buffer again is our padding of A's, the return pointer guess, followed by the NOP sled, followed by the shellcode. As you can see over here on the left, it's not done running yet. It's up to just about 4,000 tries. We'll just go ahead and let that continue. Hopefully it'll get it within 10,000 sometime. Again, though, it takes up to 15 to 20,000 tries. Now, if the randomization pool, if it was 2 to the 27th or something very high, it could take hours, it could take days or weeks to actually be successful. And as I mentioned before, if the program if it doesn't allow you to keep trying, continuously try, then one failed exploit attempt is going to crash the process, and you're likely going to get detected and not get in. But a lot of the local privilege escalation or elevation vulnerabilities that you'll see, you do get to keep trying over and over again. As long as that system's not being monitored too well, you should be able to get away with that. Now, mind you, in order to run a local privilege escalation, you have to have gotten access to that system in the first place. So we're just going to let this continue to run. As I mentioned, this particular exercise is part of a boot camp that runs on day 2, I believe, of Security 709, which is developing exploits for pen testers and security researchers. The course is now moving to a 6-day version. The new day is actually on patch diffing, Microsoft and other program patch diffing. So when new patches come out, running a differential against the patch, against the original version and the patch to see what's actually changed. Once you figure out what's changed in the code through disassembling it with IDA Pro or some other program, you will be able to see exactly where the vulnerability is located. So as you can see, we are now successful, so I didn't have to waste too much of your time speaking about things. It took 5,756 tries to get a root shell. Now, that may seem like a lot, but sometimes you'll run this and you'll get it within the first 500 tries. You'll get really lucky. One of the other methods we look at in the course, we can get it down to about 1 in every 10 tries. It's just a different method. This is simply brute forcing. So, again, thanks for watching. If you have any suggestions or comments, please go ahead and post them or send them to me at Stephen, S-T-E-P-H-E-N, at deadlisting.com. Again, this information comes from SANS Security Sec 709, developing exploits for penetration testers and security researchers, which is running quite a number of times each year. So go ahead and check it out on the SANS website. Thanks.